Yes.
Yes,
Good evening. Good evening to everyone. Thanks for Michael, first of all, for we met and we get a very, very good relations in summer. And I'm really happy to contribute to this activity, which I hope will finish with the monument of Adelard. And I really like an idea to build it in a symbolic way with the use of Platonic Dodecahedron. And all this event is called today Adelard and the Platonic Solids. And I suggested a long title of my talk, which I show in a couple of minutes, but I really like this short title, Adelard and Platonic Solids. I will, in my lecture, I will very shortly talk to Adelard, but I should do it. I should, because he's very unknown person, and the credit, he should get a great credit as a first English scientist, and also one of the basic scientists in all our civilization. So Adelard of Bath was English natural philosopher of 12th century. Most of his life is unknown. When we talk about numbers of years of his birth and death and writing manuscripts, it's all approximately. He's known both for his original works and for translating many important Arabic and Greek scientific works of astrology, astronomy, philosophy, alchemy, and mathematics. The oldest surviving Latin translation of Euclid Elements is 12th century translation by Adelard from an Arabic version. This will be a main topic of my talk. And I will explain, you will understand why. Also, it's very important that this translation of Adelard was the basis of the first printed book of Euclid Elements, and maybe the first printed book in mathematics at all. He is known as one of the first to introduce the Arabic numerical system in Europe, and also ideas of algebra. His stance of the convergence of three intellectual schools, the traditional learning of French schools, because he learned in monastery of Tours. We should know that it was a time when there were no universities. The knowledge and science were around the churches and monasteries. French school, Greek culture of southern Italy, and the Arabic science of the East. Yeah, I also will very shortly mention his main manuscripts, and the very first was a trio of dialogues written to mimic in Platonic style. All three is written as a correspondent with his nephew. The first was called On the Same and the Different, and the second one is very, very important for us. It's questions of natural science. It's really basics of the future natural philosophy. And the third one in this trio was a treatise on birds. He also, before his traveling to the East, he probably before, he published the book Rules of the Abacus. And then he took his famous travelings. He started from southern Italy, then Sicily, and then what is called lands of crusaders, Greece, West Asia, Syria, and Palestine. And then we come to his translation of Euclid's Elements. Again, which will be mostly focused on, that's why the Dodecahedron can be important for. Okay. Not less important, a translation of astronomical tables of Al-Khwarizmi, which called Zich, the first widely accessible Latin translation of the Islamic ideas about algebra. When he came back to Bath, he probably died in Bath. He also wrote the Astrolabe treatise. Now I need to tell a couple of words about Euclid himself. Yes, he lived around 300 BC. The main father of geometry, and the Elements also maybe was written probably around 300 BC, and this may be the main book of our civilization, at least one of the main books. And this was consistent of 13 books, and its collection of definition, postulates, proposition, theorem, and constructions, and mathematical proofs of the proposition. And this was suggested first by Euclid. I need to say that the simple translation of something like Euclid elements was known before Adelard. But Adelard first did the complete translation, and he introduced to Latin world the idea of proving of theorems. In my context, in context of my talk, it's very important, book number 13, in which Euclid constructs 5 regular Platonic solids. The great Darcy Thompson, the great British scientist, and I can also talk 1 hour about him, but if somebody is interested, we can discuss it later after my talk. He said, Euclid never dreamed of writing an elementary geometry. What Euclid clearly did was to write a very excellent account of regular solids, Platonic solids, for the use of initiates. What he means that the entire book is just introduction for the introduction of Platonic solids. Yes, I also put these 2 episodes, let's say, 2 parts of the great frescoes by Raphael in the Vatican, the School of Athens. In one you see Plato and Aristotle. And for Plato, Raphael used as a model Leonardo. And he used, and the left one shows Euclid. And for this, Raphael portrayed the great architect Bramante. Now I come into my talk. Yes, my long title is Geometry Behind Nanotechnology. From Plato, Archimedes, and Euclid, via Adelard of Bath and the Renaissance scientist, to discovery of Fullerene. Yes, I worked for many years already in Ben Gurion University of the Negev. And you know that Israel is a very, very small country, and 60% of our territory is occupied by the desert, which is called Negev. And for the name of our university, you understand that we are in the Negev. And also you can see the beautiful photo of our campus. This is the southern campus, because the main campus is in the city which is called Beersheba. But our campus, the campus of so-called Jacob Blaustein Institute for Desert Research, is situated just in the middle of nowhere, in the middle of the desert Negev. And my main profession is development of new materials and devices for conversion of solar energy to electricity. And for many years, I studied materials based on a carbon molecule which is called Blackminster Fullerene in a form of truncated icosahedron. This is, you can see Leonardo picturing of this shape. And you can see also Dürer drawing of sun and 2 arrows in 2 different directions, means that we in our lab, in my research, we use both, we go in both directions. We use Blackminster Fullerene to create solar cells, and we also use solar energy to synthesize these nanomaterials. But I will not talk today about it. It's just my main reason why I'm interested in the history of polyhedron. And let me just give you a couple of definitions. My aim is that everyone understand it, even if you have no any background in mathematics, physics, or chemistry. When we talk about polyhedra, I mean that polyhedron is a 3-dimensional shape with flat polygon faces, straight edge. Can you see my mouse? I can do better. One second. Okay, let's do it this way. Yes, straight edges and sharp corners or vertices. Yes, then you can see 3 polyhedron, which is tetrahedron. This is one of Platonic solids. and cube and other Platonic solids, and truncated icosahedron, which is Archimedean solids. Yes, when we talk about this material, fullerenes, we talk about the third allotrope of carbon. For many, many years, we, human beings, know only two crystalline modifications of pure carbon. It's graphite and diamond, and I'm sure that all of you know about it, yes? But in 1985, this molecule, carbon-60 or Blackminster Fullerene molecule, was discovered in the form of this truncated icosahedron. And to understand it, to understand this idea of this structure, we should come back to the structure of graphite. Again, this graphite is very interesting and very strange materials. It has so-called big anisotropy because in a one plane, which we called graphene today, it has a very strong chemical bonding and very weak bonding in it, and this is a closed packing of hexagons, but it's a very, very weak bonding between the layers. That's why we can write by our pencils, for example, because it's exfoliation of these layers. Yes? So in 1966, the very interesting personality, his name is David Jones. Actually, he's not a scientist, frankly speaking. He published once a week an idea, first in a journal which is called New Scientist, and now many, many years in Nature. And then many other scientists work on these ideas, a hypothesis, and number of Nobel Prizes got it. Some ideas was not realized. What he suggested, that implanting of pentagonal defects, pentagon, in this hexagonal graphene layer might transform this flat layer into a giant closed cage molecule of carbon. And this was theoretically developed by Japanese scientist Eiichi Ozawa and two Russian scientists, Dmitry Bachwar and Yelena Galper. But it's interesting story about Ozawa paper. He published it in Japanese, and then he translated all his papers in English, but not this, because he believes that it's not important. But after the Nobel Prize was given for the discovery of this molecule, he realizes maybe he was wrong. It was also, before the discovery of fullerenes, it was also published mass spectrum of different, you can see it, I will explain what it is. It's a different carbon clusters with different size, with different numbers of carbon atoms in this. And you can see that the maximum is carbon 60, the next is carbon 70, but all these carbon clusters or molecules, let's say, started with carbon 36. It is even numbers. And I will explain you mathematically why all fullerenes should be even numbers. But then in 1985, British scientist Harold Crotter, he was very interested in astronomy, in astrochemistry, and he came to another guy, both of them unfortunately died already, who developed the system for study carbon clusters. An idea of Crotter was to study something in the lab and compare, study carbon clusters in the lab and compare them with something reading from in astronomical observatory. And the experiment was the following. They used rotating graphitic layer and ablation it with laser, creating atomic plasma, carbon atomic plasma. And then one night, and Smalley told him that he's very busy, lab is very busy, he can come to the States, but he can work only during nights. He gave him one student, but he works 2 weeks during nights. And one night they found a predominance of the peak of carbon 60, and the next is carbon 70. And this what means that they really see the unknown molecule. And they have no any information about structure, but they suggested the structure of truncated icosahedron. This is like a modern soccer ball. It's today we understand that this is one of Archimedean solids, but This polyhedron has 60 vertices, carbon atoms, 32 faces, 12 pentagonal and 20 hexagonal, and 90 edges. And edges are of two kinds. One is edge between two hexagons, it's double carbon bond, and one is between hexagon and pentagon. And they gave a name, Blackminster Fullerene, after American architect Blackminster Fullerene. So after the discovery, 5 years after discovery, the structure was proved, and in 1996 they got a Nobel Prize for discovery of this molecule. In a Nobel lecture, Harold Krotter said, the story of C60 cannot be recounted without reference for its beauty, which it came from the incredible symmetry. So, yeah, I need also to explain what the symmetry means, because I promise you to explain everything, not to use any scientific, symmetry, again, is from Greek, and it means agreement in dimensions, due to proportion or arrangement. In everyday language, refers to the sense of harmonies and beautiful proportion and balance. So you can see two beautiful images. One is Leonardo Vitruvian Man, and another one is a drawing of Harold Krotter. He embedded Leonardo's Vitruvian Man in C60 molecule, actually not in C60 molecule, but in Truncated Icosahedron, when he gave his inaugural lecture. The word symmetry was suggested first by sculptural of 5th century BC, Greek sculptural, of course. His name is Pythagoras of Rhegium. And, sorry for this Russian word. He also suggested the word asymmetry. Asymmetry is, if you understand what is symmetrical, asymmetry, it means there is no symmetry, yes? We don't know any of his sculpture, it not survived, but we know beautiful sculpture of his pupils. For example, this Chartier of Delphi, which is in Delphi Archaeological Museum. But we all know better other Pythagoras, Pythagoras of Samos. Actually, Pythagoras of Rhegium, he was born in Rhegium, but he also lived most of his life in island Samos. Pythagoras of Samos didn't use word symmetry, but he used the word harmony. And of course, he understands that if you have an AB and it divided by point C of two equal AC and CB, this will be a symmetrical or harmonic way. He also introduced, or maybe used already, golden ratio. And what is important for us, in Euclid elements, golden ratio means 17 times, sorry. In mathematical, symmetry has a more precise definition and usually used to refer to an object that invariant under some transformation, including translation, reflection, rotation, or scaling. You can see, for example, a beautiful example of reflection symmetry in a triangle and is in a Taj Mahal in India. For us today is more important so-called rotational symmetry, and C60 molecule or truncated icosahedron belong to so-called icosahedron group of symmetry, which is the most symmetrical group, and it has all kind of rotational transformation, twofold, threefold, and fivefold. Then Krotter suggested that another important aspect of the molecule is aura, which comes from his name, Blackminster Fullerene, and the direct association with the Geodesic Domes designed by Blackminster Fullerene. It invests this elegant molecule with a charisma that has fascinated scientists, delighted people, and has infected children with a new enthusiasm for science. Before I come to my main topic, Archimedean and Platonic Solids, I need to tell a couple of words about Blackminster Fullerene and to explain why the name of the guy who died 2 years before the discovery of this molecule can give a charisma to chemical molecule. If you look on Encyclopedia Britannica, you can read that Richard Blackminster Fuller was architect, philosopher, engineer, inventor, author, cartographer, geometrician, futurist, teacher, and poet, one of the most original thinkers of the second half of 20th century. And I really believe that that's true. It is. In 1927, when he was in a very difficult situation in life, he decided to give all of his life for the aim which he formulated and as a non-profit search for design patterns that could maximize the social uses of the world energy and industrial resources. In the simple words, he decided to find a ways how to build stronger, better, with less material, with cheaper material, with more simple materials. And then he formulated his aim in the language of mathematics. First of all, he believes that our Descartes system is wrong because it's based on a cubic architecture. And all we live in a cubic architecture. If you look on a room, you will see cube, yes? But Fuller formulated the square and a cube in 2D and 3D as the most unstable structures. What is the most stable structures, according to Fuller, is triangles and tetrahedron. He always gave a reference to this tetrahedral configuration of carbon bonds in sp3 hybridization. But if you want to build a cube or square stable, what you need to do, you need to divide it, a square by two triangles by diagonal, and it will be, and the same you can also inscribe tetrahedron, inscribe this cube, and then you will give it stability. Then he came to the idea of geodesic domes, which consist of many, many triangles, and triangles are grouped in pentagons and hexagons, exactly like in Blackminster Fullerene molecule. So you will see this, one of his main famous buildings in Montreal. It's American Pavilion on World Exhibition Expo 67. You can even visit it today. It's a Museum of Environment or something like this in Montreal. It's very interesting. Now we all lived in a COVID era, yes? And a COVID is so-called spherical viruses. And today we know that all viruses are of two groups. One is just helical, but spherical viruses all has icosahedron symmetry. In my language, it's Fullerene-like structures. And Fuller, the first paper about it was done by Donald Caspar and Aaron Klug about these structures. And in this article, this first article, they gave a very strange acknowledgement at the end of the article. The solution we have found was in fact inspired by the geometrical principle applied by Blackminster Fuller in the construction of geodesic domes and his physically oriented geometry of efficient design. Aaron Klug, by the way, he was a president for many years of Royal Society, but he also was a very good friend of our university, and I talked to him about the Fuller involvement in their discovery, and he really confirmed it, that yes, they met Fuller, and he really insisted to use these structures to describe viruses. Now we come to our main topic, polyhedron in science and fine art. In a Nobel Prize lecture, Smalley said that Archimedes was the first researcher of truncated icosahedron. Why? Because this truncated icosahedron, this is a polyhedron number 4 in this picture, is only one of the family which consists of 13 polyhedra, 13 solids, which we call today Archimedean polyhedra or Archimedean solids or semi-regular solids. What it is? Yeah, this picture is, you can see this picture, is from the book of Johannes Kepler, Harmonies Mundi, published in the beginning of 17th century. Archimedean solids has all faces of these solids are regular polygons, and all vertices are in symmetrical equivalent position, like carbon atoms in this number 4 and C60 molecule, yes? But Archimedean solids consist of at least 2 different types of polygons. For example, in my number 4, it's pentagons and hexagons. And that makes them different from so-called regular polyhedra or Platonic solids. And this we only know only 5 of them, Platonic solids. Actually, I believe that the name Platonic solids is wrong, and mathematicians prefer to use regular solids instead of Platonic solids, but never mind. It's only tetrahedron, cube, octahedron, icosahedron, and dodecahedron. They consist of only one regular either square or triangle or pentagon. And starting with Plato, let's see that Plato is also, he lives in 5th and 4th century BC. And four regular solids, tetrahedron, cube, octahedron, and icosahedron, was known to him. And actually, probably even before 1 century before him, to Pythagoreans also. Plato didn't describe them. The first guy who really described all 5 Platonic solids was Euclid in the Elements. But Plato associates these Platonic solids with 4 so-called classical elements: fire, earth, air, and water. And then the 5th element, quintessence, yes, the 5th element, was discovered probably by Hipparchus. Aristotle also mentioned it. And it was associated with the space, with universe, with cosmos. If you think about these four solid elements, yes, you can also think about our physical understanding of matter today. We can say the same. Fire is plasma, earth is solid. Oh, I'm sorry, you need to exchange, it's a mistake. Air is gas, water is liquid. And what about the 5th element, quintessence? Good question. It's space, of course, universe, yes? But I think that when we really think about modern scientific paradigm, it's better to use not plasma, solid, liquid, gas, but space, time, energy, and matter. If we use this for quintessence, it's better to use light. Why light? Because light unifies everything. It's unified space and time. When we look in the space, on stars in the space, we see just light from them, which were generated and come to us during long time, many years on the way. So light is also unify energy and matter. So the light is real quintessence. Yes, and then starting from Greeks, this quintessence was associated with Dodecahedron. That's why I really think that it's the idea to build a Dodecahedron as a monument to Adelard. And I didn't mention it, that we didn't know how Adelard looks like. All his drawing is just very approximate drawing. Yes, and this is a great idea. I really like it because, again, we all knew it from Euclid Elements, and Adelard of Bath make a real effect on knowledge in Europe of these 5 Platonic solids and Dodecahedron in particular.
I can take this somewhere else if you want me here.
Sorry? Yes, please look on this table, which summarize some parameters of these 5 Platonic solids: tetrahedron, cube, octahedron, icosahedron, dodecahedron. And these parameters is ages in each phase. For tetrahedron, it's 3, it's triangles, yes. Cube, it's 4. Octahedron, icosahedron, it's again 3. And dodecahedron is 5. Age that connects in each vertices. Again, some phases, ages, and vertices. And also I put its F minus E plus V. And you see that all this is fantastically equal to 2. Why it's equal to 2, I will talk later. But let's understand something which we can read from this table. First of all, you can see that if you think about cube and octahedron, you can see that ages in cube is 4 and 3, and octahedron is 3 and 4. Faces and vertices 6 and 8, and this is 8 and 6. The same for icosahedron and dodecahedron. And mathematicians call this dual polyhedron. So they say that cube is dual to octahedron and vice versa, and icosahedron is dual to dodecahedron and vice versa. The dual polyhedra have the same symmetry. From the point of view of topology, symmetry, let's say physics also, icosahedron and dodecahedron are the same, the same polyhedra. But tetrahedron is dual to himself. We can also understand how to build Archimedean truncated icosahedron from Platonic regulated icosahedron. What we should do, we should truncate near to every vertex by plane. And the question, we will produce new faces, but which one? Let's see how many edges come in icosahedron in every vertex, 5. So our new faces will be pentagonal. But how many? Let's see how many vertices we have in icosahedron, 12. So we will produce new 12 pentagonal faces, and the rest 20 will be hexagons. And then we will get this modern circular ball structure or carbon 60 structure, Blackminster Fullerene structure. Okay. We go next. 1 second. Yes, this is a very important picture which is used in a lot of literature in Fullerene. This is Leonardo drawing of truncated icosahedron. Leonardo did this as illustration to his book, to the book of his friend, monk and mathematician Luca Pacioli, and the book is called The Divine Proportion. Yes, the Divina Proportion. The Divine Proportion means golden section. Leonardo was great in every direction, and he invented a way. This was the first three-dimensional image of any polyhedra in science. You can see that he produced more than 50 images of different polyhedra. This skeletal way, I call it, we call it today method of solid ages. And you can compare it, this Leonardo's method of solid ages, with his also method of solid faces. This is much better, the left is much better. But if you draw edges just by lines, as we usually draw in 2D, it will be a big mess. So it was a very big suggestion for knowing and learning of polyhedra. Actually, I can show you the beautiful examples I found this summer near the bus, near Bath. The first is also in monuments. The first in Salisbury Cathedral. It's a monument to Sir Thomas Georges and Lady Georges, of course. You can see both Platonic and Archimedean Solids. I can show you in a big space. You can see at the very top universe, symbol of universe is Dodecahedron, and then you can see 2 icosahedron as well, but you can also see Archimedean solid. This is called cubo-octahedron. You can see that these 2 faces, 2 types of faces, squares and triangles. Nearby to this famous monument and famous cathedral, there is a small church in a small village in called, just a second, let me take this out. I'm sorry. I have a problem. In Wimbers, it's called the Church St. Gill in Dorset. And this is a monument on Sir Anthony Ashley and Lady Ashley, of course. Both is in Baroque style. But what you can find, surprisingly, a beautiful image of truncated icosahedron. You see, it's also like like a symbol of space for me. It's like these hands, very strange, it's like cracks of astronauts. But when you think about this Leonardo way, it's really beautiful and powerful way to show polyhedra. I suggest to think about your monument, maybe also use the Leonardo way of skeletal polyhedra when you will build your monument in Bath. Yes, who was this Luca Pacioli? He was a very, very controversial person. Why it's controversial, I will mention in a moment. But we certainly know he was a monk and mathematician, and wrote a number of great manuscripts, great books. But we certainly know how it looks like, because there are numbers of, at least a couple of great portraits of him, and one you see by Jacopo de Barbari. And Luca Pacioli looks on the Archimedean solids, which is called rhombicubo-octahedron, which he discovered. What I didn't say, I must say it, that similar story to Platonic solids, even worse story with Archimedean solids. The Platonic solids, all known was even in medieval time in Persian and Arabic culture, and after Adelard of Bath in 12th century, Europe knew them. What we knew today, Archimedean solids, the work of manuscript of Archimedes didn't survive. We didn't know it, didn't find it in the very end. There is no manuscript. Maybe it was happening in the big fire of Alexandria library. We don't know. And in the Europe culture, in Europe, it was rediscovered. All 13 bodies were rediscovered in the Renaissance time, much later, at least 2 centuries later than work of Adelard of Bath. And most of this rediscovery was done by great artists. You will see it. I will show it. But now we know that number, not all of 13 Archimedean solids, but number of them was known to Arabic mathematicians, Persian mathematicians. So one of these rediscovery was Luca Pacioli, and he rediscovered rhombicubo-octahedron. And there is a guy who stayed behind him, and there is a big discussion, who is this guy? I don't believe so, but some historians of art believe, actually you can see also this beautiful dodecahedron, yeah? But some believe that this is Albrecht Dürer. We don't know it, but he certainly met with Barbari, and he certainly went to learn. He was also one of the greatest mathematicians of that time. 3 years before his death, he he wrote 3 manuscripts. He also rediscovered one of Archimedean solids, and he also suggested, very interesting, he was one of the first who did these flat nets of, you can see, flat net of dodecahedron and flat net of truncated icosahedron. And it's interesting that today we all use, people who work with crystals, with molecules, mathematicians, all use this Dürer's idea. Yes, but why Luca Pacioli was controversial? Because he was a pupil, he was a student of the greatest, one of the most great Renaissance mathematicians, and one of the most great Renaissance artists, Piero della Francesca. And today we know that in a manuscript of Piero della Francesca, it was the first description and first image of truncated icosahedron. But Luca Pacioli published the book. It was also printed without mentioning. He just copy and paste this small manuscript by his teacher. But never mind, we gave this credit for both. I gave a credit for Luca Pacioli also because of work of Leonardo, this 3-dimensional image. You can see in Milano this beautiful painting by Piero della Francesca, and the guy who stayed The second from the right is Luca Pacioli. This is interesting. Yeah. Also interesting that they both come from the same city in Tuscany. It's a small city called San Sepolcro. And there is a street of Piedra Francesca. There is a monument on Piedra Francesca near to this street. But what I'd like to look your attention to, put your attention that he stayed on the book, and you see what the book is. It's Euclid too. It's Euclid. He stayed on Euclid. But nearby, there is a monument to Luca Pacioli. Also, this monument is nearby to the monastery. He was Franciscan monk, where he lived for a long time. And nearby, there is a private garden. And in this private garden, you can see this sculpture. My wife told me, look, this is Luca Pacioli staying on Pier della Francesca shoulders. Maybe. But I think for your monument, and I really want to see this monument built in Bath, it's also very important a plaque, a memorial plaque, which saying something in strong words about Adelard of Bath. And I would like to show you an example how Italians did it. They did it as a poem. So it's two memorial plaques very nearby, maybe 3 minutes one another. One is on Pier della Francesca and one is Luca Pacioli. I will read English translation. It's in Italian, of course. In honor of Pier della Francesca, in the 15th century, the sovereign painter from whose mastery Perugino learned the marvels of art and Italy the geometry principles of perspective, here where her great son lived and where at 82 years he ascended into the heaven, this memorial is placed in the year 1876 by a grateful and reverential country. A country means it's not a state, because there was no state for that time. Not state Italy. Maybe reverential city. To Luca Pacioli, who was friend and consultant to Leonardo da Vinci and Leon Battista Alberti, who first gave to algebra the language and the structure of science, and whose was the great discovery of applying it to geometry. The people of San Sepolcro, upon the initiative of the Society of Workers, ashamed of 320 years of oblivion of the great fellow citizen, placed this memorial in 1878. I think it should be done something like this. Yes, then if you look on these 13 Archimedean solids, you can see that most of them were rediscovered by Pier della Francesca, two by Luca Pacioli, 2 by Dürer, and 1 by Daniele Barbari, and the very last one by Johannes Kepler. But Johannes Kepler was also the one who described the entire family and gave names which we use today, give them modern names. And this was done in his great book, Harmonis Mundi, where he also published his famous third law of Kepler law. Yes, then after a century, the great mathematician, one of the great mathematicians of all times, Leonard Euler, suggested the theorem how we can connect a number of faces, edges, and vertices. And he says that for any convex polyhedra, number of faces minus number of edges plus number of vertices must be equal to 2. Actually, this theorem was almost formulated by Descartes a century ago, but it was a detective story what's happened with Descartes' manuscript. I will not mention it now. But let's think what I can say that using this formula, we can construct entire family of fullerenes. I told you that the most stable and most famous fullerene molecule is Blackminster fullerene, carbon-60. But there is entire endless family of these molecules, which definition are closed case molecules of pure carbon in the shape of polyhedra with only pentagonal and hexagonal faces. Now it will be very simple mathematics, arithmetics, I would say. If we use this, if faces are only pentagonal and pentagons and hexagons, F will be P plus H. But because two faces come to one edge, double number of edges will be 5P plus 6H. And because three edges come to every vertex, triple number of vertices will be again 5P plus 6H. Now what I'm doing, I multiply the first equation by 6, the second by 3, and the third by 2, and take first minus second and plus third. And what I get, you can do it by yourself, and you can find that this 6F minus E plus V will be equal to P. H, number of H disappear. But from Euler's theorem, we know that F minus E plus V should be equal to 2. What does it mean? That in any structure, it doesn't mean it's a dome or a Fuller geodesic dome, or it's a virus, or it's a molecule. In every structure, which only pentagonal and hexagonal faces, number of pentagons might be equal to 12. And then we can reconstruct, we can add H, and number of vertices will be all even number. And then we will see what will be then the small, we can reconstruct the entire family. What will be the smallest Fullerene? Dodecahedron, which consists only of 12 pentagons. This one. Then if you think about you remember my experimental results, I show you all Fullerenes has even number, and then the smallest one is your dodecahedron. But then the question is why C60 is more stable and then C70 is more stable? Because it's the smallest Fullerene which satisfied to so-called isolated pentagon rule, where every pentagon is a defect in chemistry. Organic chemistry does like pentagons. But in C60, every pentagon is surrounded by a ring of 6 hexagons. There is no any common border between two pentagons. The next such molecule is carbon 70. And another reason for this stability is symmetry. Because chemistry really likes the symmetry, because if you have any chemical imperfection in the molecule, if it's symmetrical, it's delocalized on all over the molecule. Then if we add 10 additional atoms, we got C70 at the equator, and then C70 is not buckyball anymore, it's not soccer ball, they call it rugby ball. And you know, so beautiful symmetry like in C60. If you do it 2 times, we get carbon 80. But if you do it many, many, many times, we got what we call today carbon nanotubes. And then I come to the idea that these two discoveries, discovery of Fullerenes and discovery of carbon nanotubes, was a real trigger of the modern nanotechnology. And then I would like to suggest you, I'm finishing. I would like to suggest you my schematics that how it was going on, starting from Plato and Archimedes and Euclid, and then this Persian scientist who translated Euclid book to Arabic, and then it's this knowledge from them. I should put this arrow again. It's come to Adelard of Bath, and then from Adelard of Bath to Pier della Francesca, Luca Pacioli, Leonardo, Dürer, Kepler, and then with Ehlers to Fullerene science and nanotechnology. This is a mathematical race, a geometrical race of idea. But if you think about different direction, Adelard of Bath, which in his natural philosophy, his own manuscripts, was really affected by Plato. And then Adelard of Bath affected Roger Bacon and Francis Bacon, and Roger Bacon, Francis Bacon, and then via Newton, they affected natural philosophy and modern science, which again affected nanotechnology. And I need to also mention Kepler, who was in both directions, in scientific, which was really a predictor of Newton, and in geometrical. And that's I finished, and thank you very much for your attention.
Wonderful. Thank you very much, Eugene. That was absolutely fascinating. So a little round of applause for that talk. Thank you very much. Zoom applause are never quite the same as the real thing, are they? But thank you.
I think I should
Stop sharing. Yeah.
Stop sharing. Yeah.
Fantastic.
If we need it, I can open it again.
No problem. And I would invite everyone who would like to put their camera back on so we can see happy, smiling faces. So I'll kick off with a bit of a layman's question, Eugene, but I'm sure there'll be some more technical questions to come. John, if you go to gallery view and you can see everyone, you'll see John Law demonstrating the Platonic solid. Excellent.
Yes, exactly.
So just
in Leonardo way.
Yes.
By Leonardo techniques.
Yeah, here's the other kind.
Yes, this is the other guy. I prefer the first one.
Yeah, me too.
Eugene, why do you think Adelard is so little known, even in his own country, even in his own city?
Good question. It's not a question to me. I really don't know. This is a problem. First of all, he lived maybe too early. We know what's happened in Renaissance now much better. Yes, and he was 2 centuries before this big revolution in Renaissance. Big interest in Renaissance to all Greek manuscripts and also to Arabic manuscripts. It was continuous. I don't know. I think you should have another lecture by the historian about the fantastic life of Adelard, and controversial, of course. He was lived before universities, before scientific era. Maybe this is an answer, but I think we should. That's why I really like to contribute to give him a credit.
Well, I know that's partly the work we're doing here, driven by Michael Davis, is to really bring him back to the centre again of everyone's attention.
Really
so I'm very keen on that. So, can anyone else with any questions from anybody? Please raise your hand. Is that Betty? Unmute.
I liked your chart that you just showed us with the arrows of where he got his data. But there shouldn't be the line between Plato and Adelard at all, right? It should have all gone through the Middle East.
Yes, of course. It should be a lot. Aristotle, even before the Middle East, Aristotle should be there also. Yes, of course. But because I talk about Platonic solids, the Plato himself was important for me. But every schematics, it's a simplification. Yes, I think it was okay to do this. But of course, I agree for sure.
Well, I just would like to have that because I think that would be a very useful diagram for us to be using when we talk about Adelard.
Exactly, I agree.
And can I invite any more questions? I'm sure there are some people here who may be able to comment on the geometric and mathematical side of things. I'm not one of them, I'm afraid, but I'm fascinated by the Adelard story. Anyone? Michael, do you want to perhaps tell people a little bit about a bit more about our plans for Adelard?
Yeah.
Yes. We want to go for a planning permission for this memorial to go up in the Keys development. Of course, Adelard's, he would have known the medieval city within the old Roman walls. And that is where our Adelard activities have been focused previously. But now Future Bath is developing along the river. This is Future Bath. And we find that the North Keys development, which is first development out along the river, that is a perfect opportunity for us. The logic being that Future Bath is the relationship between that and its distinguished past. But as you say, the problem is that people have no idea about Adelard and his importance to science, to the history of science. And so we've got a lot of work to do, but I think we found that when people are informed about this man, they are all immediately absolutely intrigued, because it's a wonderful story, and it really raises Bath and the rise of science to a different sort of level. And the future Bath is going to be significantly technology-driven, high-tech, knowledge-based, creative industry. That's what we're after. And what better base on which to have that than the story of Adelard, and particularly this Dodecahedron, which is such a perfect representation of him.
I think that, Eugene, you brought that out while in the talk as well, how it's sort of linked. You've got this fairly ancient figure, but working in an area that is so relevant today in nanotechnology and elsewhere. Sort of putting some of the stepping stones along the way that's led to scientific work that's going on this very day. And I think that's what's useful for Bath. I mean, I know, Brian, you've thought about this a bit, is that Adelard is a link between the past and the present, or could be conceived as.
Yeah, I mean, I'm particularly fascinated to see the comparisons made with great works of art, like with David, Leonardo da Vinci, or even the Taj Mahal in India, all of which seem to have a link back to the whole elements that Adelard seen in the Euclips, I think would be the correct area, that he was translating all of this and able to see from the scientific side of things how that developed into great works of art in our more modern era, at least of the 17th century and onwards.
Yeah,
it's a strange affinity at the edges between science and art, and that is really the area in which Eugene, that's his passion. And of course, the Dodecahedron is a perfect example of that.
I mean, I think you'd be interested to know that, Eugene, that we're planning an exhibition probably in December. And I think we'd love to use some of the various elements from your presentation within that exhibition, if you were happy with that.
I would be happy to share, and I hope that we can come in December. Maybe it will be better time.
That would be even better.
Well, that would be wonderful if we could make that happen. Thank you. Yeah, that would be fantastic. Cool. Anybody else got any questions? Okay, well, I think we can thank Eugene for a fascinating talk on a fascinating figure. And we'll hope to see you in December.
I thought that Eugene's visual aids were beautifully constructed, very easy to follow. I mean, it was a lovely talk. And as you say, the visual aids are particularly instructive.
So actually, I do have one question, Eugene. When you came to Bath previously, I know you touched on this briefly, but what brought you to Bath? Was it specifically this research, or was it?
Yes, it was both. I think I have no photo of Petra, but I think she's my colleague from University of Bath. I don't know. One second. Petra, can you hear me? No, really.
She's on, but she's muted.
No, I visited two scientists in University of Bath on my walk on photovoltaics, and not connected to this talk. And but we also have a friend living in Bath, so we stay for him. But I show you two photos of monuments I wanted to visit and to photograph, of these sculptures, which is in this kind of interest. I also visited Cambridge and Oxford, and I saw also Snezhana Lawrence from Cambridge. That she's a historian of mathematics. So I would say it's because of my both interests in different. Now we can maybe no. It's Petra is muted.
Sorry, I'm on my phone, so I don't know if you can hear me. I'm here.
Yes, we can, Petra.
No,
Thank you.
I just want to understand if you are Petra Cameron.
Yes, I am. Yes.
Yes, she's a professor in the University of Bath in chemistry department.
Fantastic.
We have a joint interest in another material which is called perovskite solar cells. Perovskite for the water.
Well, Petra, we'll keep you informed of developments with our plans for Adelard and the reception that's coming up in December.
That would be fascinating. It was a really, really interesting talk, Eugene, as well. Thank you.
Thank you. But I would like to say that I decided to talk about these nanostructures when Michael told me that the monuments will be in this new business or high-tech area. And I thought, maybe it's a good idea to connect everything together.
We actually have a question in the chat, Eugene, actually it's from the classical period. It's from Seperi Audi. Do you happen to know where Adelard learnt Arabic?
No, we all know that he learned everything during his traveling, more than 10 years, traveling in the area which all spoke Arabic that time. The good question is, if he knew Arabic before that I don't know. I know that he was educated in Tours, in monastery of Tours in France. Did he learn Arabic there? It's a good question, but it's not to me. I don't know. But I think most probably he'll learn it on the place.
Yeah, exactly.
Incredibly, but you think of his achievements in that time, and even just I know we talked about how he travelled to Antioch.
Another very interesting question, which was discussed in literature: who paid for his traveling? And one of the answers is then he's boss of Tours, and then he would become a boss of Bath also. He paid for this. This was traveling just for knowledge, not everything else, not trade, not military purpose. This is amazing.
Amazing story. Well, on that note, thank you, Eugene. Thank you, Michael, for your introduction and your comments. And thank you to everyone for attending tonight. It's been a lot of fun. And there is going to be lots more to see and hear about Adelard as we move forward. So, again, thank you for all your involvement. And if you want to watch this again or sections of it, it will be coming up on the YouTube channel in a few weeks' time, and perhaps offline, Eugene will ask you if you're happy for us to use some sections of your presentation. Perhaps you can send us a copy of that.
Yes, sure. I can share everything.
Fine. Can we have a Zoom round of applause? Thank you very much, everyone. Okay. Thank you, everyone. Good night.
Good. Right. Yeah, fine.